Hey, what's up, guys? Welcome to my own complexity video. On previous I talked about computational complexity of the interactive proof, but talking about is deterministic interactive proof. The next continuous three videos that I will prove the famous results. Basically, the proof the interactive proof complexity class is the same as the p-space complexity class. I think this is like the first famous, I think it's very famous results, because in the complexity theory, it's very difficult to prove that two complexity class is the same. As far as I know, that IP equals to P space is the first one that I think is very amazing. Okay, and if X, so recall that the interactive proof basically means that the prover, right? So the prover is a polynomial time Turing machine, and the probabilistic, and the verifier is a polynomial time Turing machine, and but can throw the probability and has the probability, and the prover is all powerful, and the prover will send a message, and the verifier will reply for the message, and they keep going, and they can do the polynomial rounds, and if X belongs to L, there's a prover message. There's an interactive protocol such that the probability that prover convinces the verifier is higher probability. If X do not belong to L, then for all prover strategy, then basically the prover cannot cheat the verifier. And if both satisfy this criterion, then we call that L belongs to the IP. Okay, so famous results that IP equals to P space. And so in this video that I'm not gonna to prove this in this video, but I will just first give you like one famous example, basically the non-graph isomorphism. I think this is the canonical example, but very interesting. The non-graph isomorphism belongs to IP. Okay, this is like the idea. Okay, so let's talk about story. By talking about complexity, interesting that sometimes that we talk about story, so we're not like proving something's true. It's like not like the pure mathematics. And okay, so oh my god. Okay, so if someone right, so story is like a given G, right? So it's given to graph G1, G2. Then obviously that we can define then we can ask whether G1 and G2 are isomorphic. Okay, as a graph. Okay, so for example, these two graph is the same as these two graph, right? Because you just flip this. So for example, it's 1, 2, 3, 4. This is 1, 2, 3, 4. Then all you need to do is just right, there's a map, right? You can just map 1 to 1, then maybe 2 to 3, and then maybe 3 to 2, and then 4 to 4. Right, and if you do this, then you can see that this becomes the same graph. Okay. So this is the language. It's called ISO. So ISO is given a pair G1, G2, and the G1 and G2 are isomorphic. Okay. So right, so the question is that, okay, so up to now that we don't know, question is that we don't know whether group isomorphism is in P or not, right? We don't know. Okay. But we do know, right? There's an obvious result that isomorphism is NP, right? Because if your graph is right, if your graph G1 is and the G2 are the same size n, then we just give you the we can just have the witness, right? So witness is just the permutation of the vertices, right? So just the permutation of vertices, as we just say, right? You can just give me the permutation of vertices, and I just verify the permutation of vertices such that their graph is isomorphism. So ISO is in NP. Okay. But now there's an interesting question called non-ISO, right? So I can define a non-ISO, which is if the pair of G1, G2 such that the G1, G2 are non-isomorphic. Okay. And so the obvious question is that we don't know an ISO is in NP, right? Because somehow like very difficult to, if someone want to prove that two graphs are non-isomorphism, somehow like they cannot give you the simple witness, right? Somehow like maybe they need to like tell you that the permutation cannot make G1 and G2 the same. Okay, so that means that non-graph isomorphism looks much more difficult than graph isomorphism problem. Okay. Okay, but the interesting is that an ISO has a very simple interactive proof. Okay, I think everyone, this is very simple, right? So let's, the proof idea is very simple, right? This is Merlin, and this is Arthur, right? So the idea is that, right, so Arthur just, right, someone give you a G1 and G2, then either Arthur, so the protocol first one is Arthur just flip a coin. Okay, so let's say head. If it's head, then Arthur like permutes G1 randomly and send to Merlin. Send to Merlin. Okay. And if it's tail, then Arthur just permute G2 and send it to Merlin. Okay. And that's it. And ask. So second is ask Merlin. Ask Merlin. Ask Merlin is G1. The graph. Let's call this graph. Let's say the graph is a G. Okay. Ask Merlin. G is isomorphic to G1 or G2. Okay, and so Merlin is a very powerful guy, right? Merlin is all powerful, right? So Merlin can solve like a coding problem or whatever problem cannot be solved in using Turing machine. Okay, so this is the problem. Okay, so Arthur just randomly flip a coin, and if it's head, then Arthur send G1. This first permute G1, right? So Merlin doesn't know G1 or not. Okay. Okay, so easy to prove the following, right? So if G1 doesn't differ from G2, right? Doesn't isomorphic to G2, then Merlin can, since Merlin is all powerful, right? So Merlin can distinguish them, right? So Merlin after one round, right? So after one round, that Arthur will be maybe convinced Merlin or not, maybe convinced by Merlin, and but if Arthur doesn't sure, Arthur can do it, right? So after like n steps n times, right? If Merlin all correct, right? Then the probability that Merlin cheats and the probability that Merlin cheats, right? So let's say Merlin cheats will be exponential small, right? Will be just this, right? Because, right? Okay. And obviously that if the graph is isomorphic, then the probability of Merlin fails, right? It will be half, right? Because if two graphs are actually the same, then Merlin doesn't know where is G1 or G2 comes from. Okay, so obviously that we can do the protocol twice. We can do the above protocol twice. Okay. Okay. So then we have the probability that Merlin make Arthur accept. Merlin made Arthur accept is 1 if G1 is different from G2. Okay. If G1 is the same as G2, then the probability that Merlin answer correctly with Arthur will less or equal to 1/2, 1 divided by 4, right? So this satisfies IP, right? Because for IP, if X belongs to L, then the probability Merlin make Arthur is 1. Otherwise, the Merlin make Arthur is 1 divided by 4. Okay, so this is the protocol, right? So I ask twice if Merlin all correct, then I just say 1. Otherwise, that 1 divided by 4. Okay, so this is the protocol, right? So this protocol will make only just using the 2 rounds. We just use these 2 rounds, right? Already make the Merlin and Arthur, or already prove that this non-graph isomorphism is really indeed in the IP. Okay, so this is a product. Okay, so if G1 is different from G2, then after twice, right? Then merging cheats is then that's equal to 4. If G1 is different from G2, then merging answer twice correctly, then answer will be convex. Okay, so this is idea of the interactive proof. And okay, so next time that we can start to prove that IP is equal to P space. Okay, in order to prove this, like we need to have some background. Okay, see you guys next videos.